The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So let me hand it over to Ankit now, and we're going to talk about color.
So I'm going to start with something that I discussed a few weeks back when we were talking about Epsilon Photography, and if you remember the slide I had back then, and this is one of the oldest ways of creating color images. You just capture 3 images over time, one with a green filter in front of the camera lens, one with a red, one with a blue filter. And from these 3 images, if you project them back on a white surface, again through 3 different projectors, one with a green, one with a red, and one with a blue filter in front of it, you will get what looks like a color image to the human eye. And this is stuff that was done more than a century ago, and you can take these images now, these individual grayscale images, and color tint them, and then again add them back together, similar to what you did for your assignment when you were adding the lighting. And you can create these digitally, and now there's a whole Library of Congress has this huge database of images that they have, by registering them, they've recreated these color images from black and white images. So this is one way of creating color in photography. Another sort of related similar thing to this is the color wheel. This is something that, again, I talked about in the previous class, and it's something that's used more for projectors. You have this color wheel rotating in front of this, probably has one if it's a DLP projector. And at any given time, you're just projecting one component of the light. You're either green, red, or blue. And the human eye actually integrates it over time because it happens in rapid succession, one after the other. So it's a little different from the previous case in which you were projecting all 3 at the same time and light was adding in space. Here, light gets integrated over time. You get the effect of color. So a third thing that I discussed in the previous class was this concept of 3 CCD sensors, where you use these dichroic prisms and mirrors, and you split light into the 3 wavelength regions, and then you have 3 separate sensors that capture the 3 wavelengths, and you get, using 3 monochrome CCDs, you can capture a color image. This is probably what's the most popular in most still cameras and also many of the digital cameras, and it's basically what's called the Bayer Mosaic. That's because the person who invented it from Kodak, his name was Bayer, and he had this patent in, I think, mid or late 70s, which describes this technique. The basic idea is that instead of having monochrome pixels, you put these little filters, tiny filters on top of the pixels, and the filters are sort of, you have 2 green filters and 1 red and 1 blue filter in a 2x2 region, and then this 2x2 thing is tiled all over the sensor. So any one pixel is only sensing one wavelength, either red, green, or blue. When I say wavelength, it's actually a whole band of wavelengths, but let's just stick with color for now. And so it's sensing just one of these 3 colors, and then they use clever demosaicing algorithms which essentially interpolate between the image that's sensed. So, for example, at a pixel which senses only red, you would interpolate between the neighboring green pixels in order to estimate what the green color is over there, while still making use of the color that's sensed over there, the red color. So what you see in most images is almost kind of, you're hallucinating the higher resolution because you're going up by a factor of 3 in the resolution in the image when you do this kind of interpolation. And
so if you have a 4 megapixel camera, and here it looks like we have, for every 4 pixels, we have 2 green, 1 blue, and 1 red. So if you take a 4 megapixel picture, how many pixels are actually taking each of those colors? Is 4 megapixel camera actually giving you 12 megapixels? Because when the image comes out, it's 4 megapixel in red, 4 megapixel in blue, and 4 megapixel in green. Doug?
No.
So what is going on?
It's, well, I mean, you get the resolution for each of those colors since they're separated in space by the other colors being in space as well.
Right. So when they say 4 megapixel, there are only 4 million pixels total.
Yeah, total. And then multiplied by
And then
color channels.
2 megapixels are green, 1 megapixel is red, and 1 megapixel is blue. And so what's the benefit of, if you compare this with the previous design, where you had 3 separate CCDs, one for each color? What's the benefit and what's the disadvantage?
Money. Cheaper.
It's cheaper, right? Yeah.
Why is it cheaper?
One CCD.
And there's less optics.
Less optics.
Alignment.
No.
Alignment is easy. What's the disadvantage though?
Less, you're blocking
Right.
light. So
You're effectively getting 1/3 the light. Because every time you sense one color, the light for other 2 colors is being thrown out. And when Mike talks a little bit later about some other multispectral cameras, this will become the biggest issue of the notion of throwing away light.
Yeah, and also, can you perfectly reconstruct the image?
Right, so that's always an issue. So most of the reconstruction, the interpolation that Ankit just talked about, is based on some assumption about the natural scene. But if your scene is not natural, maybe it's a black and white text, or you have very fine stripes on your shirt, in that case, the interpolation will not give you the right results. And you see it often, you can see this strange moire pattern.
Yeah. So one of the things they do in order to avoid this kind of thing is that they place a low pass filter immediately on top of the sensor, so that you get rid of any such high frequency details in a single color. But still you get, in many of these images you do see color moire, so you have some weird artifacts in one color channel and not in the others, or a rainbow sort of effect, and that shows up especially along near the edges and so on. Did someone have a question? So one of the things, as Ramesh mentioned, is that you are throwing away 1/3 or 2/3 of the light in doing the previous one. So there is this recent patent that Nikon recently introduced, where what they're doing is sort of combining these two notions that we just discussed. They have these red, green, and blue sensors at the pixel level, but they, instead of using 3 separate filters, they use dichroic mirrors in order to separate the light that's falling on the sensor into the R, G, and B components. So it's similar to the first 3 CCD case that they're using dichroic mirrors. They're not losing any light, but it's all happening at the sensor level. So conceivably they can build this thing in the semiconductor itself, and so it's much cheaper than using prisms outside.
Everybody familiar with dichroic materials? So it's basically a type of in simplest words, it's a type of a glass where at the right angle, if you shine light at the right angle, a particular wavelength will pass through and all other wavelengths will be reflected.
So it's essentially, I think it's total internal reflection is what it makes use of, and the threshold is different for different wavelengths of when the light is going to get total internal reflected or just keep going straight into the next material. And using a series of such mirrors, they can separate the 3 wavelengths.
And in the break, we'll have the soap bubbles, and they will demonstrate the same concept.
So one other popular, semi-popular sort of sensor design is what's called the Foveon X3 sensor. And instead of using 3 separate each pixel having a different filter on top of that, the design of this sensor is very similar to that which is used in film. So in film they actually have 3 separate emulsions, or 3 or 4 separate layers of emulsions, each sensitive to a different wavelength of light. And similarly over here they have, as you keep going down deeper into the pixel, different depths of the pixel actually are sensitive to different wavelengths of light. So the top region is more sensitive to blue, and the next part to green, and the bottommost is to red. And so a single pixel can actually sense all 3 colors, all 3 wavelengths as they're falling down on it. And the advantage is that you don't need to put this low pass filter on top of it, because instead of doing the spatial sort of multiplexing, you're doing this multiplexing in depth. So that's a big advantage. in terms of the resolution, yes, you do get, you don't lose the resolution like you do in the case of a bare filter. But so far, when they code the number of pixels that they have, they simply multiply it by 3. So when Sigma is the manufacturer that manufactures these foveon sensors, now they bought over foveon. So when they say they have a 12 megapixel sensor, it's really a 4 megapixel sensor. They just call it a 12 megapixel sensor because there are 3 elements for each pixel. So it's not clear whether that's really a gain in terms of the resolution, but definite gain is that you don't need a low pass filter over it, so you don't get these. You're able to capture much higher frequency information.
So you can't win either way, right? When they say it's 4 megapixel, traditional camera makers, you only get a 2 megapixel green image.
Right.
And when they say it's 12 megapixel,
right,
you still get a 4 megapixel green image.
Right. But one other disadvantage of this is that unlike the previous case where you can almost arbitrarily choose what filter you want over each pixel, in this case the separation between the red, green and blue channels is not as great. They apparently don't have as much control, so they need to do a lot of software processing on the image that's captured in order to separate the red, green and blue, and possibly they're doing some sort of, that works based on some sort of image priors, so you would have some image artifacts over there which might not be these moire artifacts, but you'll have some color artifacts.
And the actual profile is very misleading, because when you see this diagram on the left, the blue is basically getting everything. So it's something like, this is your blue, green and red, then the blue pixel is getting almost everything, and the green pixel is getting a little bit less, and the red pixel is getting whatever remaining is. So it's not like blue, green and red. So the picture on the right is completely misleading. It's getting some 3 values that are highly overlapped, and from that they're going to do some inversion and figure out RGB color. So in the very simplest words you can think of, the first one gets everything, the second one gets just this, and the last one gets this. And from that they can figure out what red, green, and blue is.
So, I should also say that there's nothing really holy about this RGB design. It's just that this was the one that was proposed first, and this is what's being used. It's the most common, but there are a whole number of other so-called bare patterns that have been proposed, which don't use this 2x2 tile. They have even bigger tiles, and the simplest one is red, green and blue and clear, so you get one pixel which gets all the wavelengths, and then red, green and blue and interpolations. I'm sure there are studies that compare various ones, because if you don't get RGB you need to do some sort of inversion and you would get noise in that inversion. But if you use, let's say, CMY, cyan, magenta, yellow, you would be able to get more light onto the sensor. So I'm not very sure of, I couldn't find any real studies that compare the various sensors or various...
Yeah, Kodak has done a few studies. They have it on their website.
They do?
Yeah.
It was always very... I'm not sure. So there are various trade-offs between the different kind of sensors, but this is the only one that you find in practice right now.
This would be a great class project, by the way, of figuring out which spectrum to choose depending on the scene.
Okay. So taking a step back from, this was more sort of a rehashing of what we already discussed before in terms of color sensing on cameras. It's important to look at what we are sensing when we sense light, and it's really a part of what's the electromagnetic spectrum that is actually much wider and has many other types of rays than what we are usually looking at in photography, which is the visible spectrum. And the visible spectrum of light goes from 400 to 700 nanometers. Usually when you talk about light, you talk in terms of wavelength, and in different, like in radio and microwave, you would probably talk in terms of frequency or in terahertz radiation and so on. But for visible light, you always say the wavelength, it's 400 to 700 nanometers going from blue to red. And it's interesting that this is really the only wavelength region that is almost completely, the atmosphere is almost completely transparent to it. So the sunlight that comes through it's other than maybe radio waves, almost all other wavelengths are actually occluded by the atmosphere, and this is really the most of the natural illumination that you have is in this wavelength region, which is probably why humans and most animals actually develop their are tuned for this region and not any other. And another sort of interesting thing is, as you keep going away from this or shorter wavelength, the more dangerous sort of the wave becomes. Already starting from UV, you start getting cancerous rays and so on, and then X-rays and gamma rays are even more so. But if you go for larger wavelengths, they are usually harmless.
And the way to remember that is, wavelength is inversely proportional to the frequency. And the product of the two, what's the number? When you multiply the wavelength of spectrum to the frequency of the spectrum?
Speed of light.
That's the speed of light, right? What's the speed of light?
3 times 10 to the 8
meters per second squared.
But in this class?
Per second.
foot per second.
1
Foot per second. Very good. And so the frequency is increasing as you go to the right, which means it has more energy, h nu, which means it can penetrate deeper and damage more things. So that's one easy way to remember what's going on the right. Unfortunately, the chart is flipped because we usually think of wavelength increasing from left to right, but this is really showing the frequency increasing from left to right.
So yeah, I guess the point I want to make here is that it's only this region that we are looking at, which is really, really small compared to the whole spectrum, EM spectrum, and there is lots of interesting stuff going on, especially in thermal IR and thermal, and even beyond that, in using it for imaging. And we heard using Wi-Fi for imaging also, and things like that, which is 2.4 gigahertz or something like that. So you don't have to be constrained for even creating a photorealistic or a visual image of understanding what's around us. We shouldn't be limited to visual sort of the visual spectrum. It's okay to think outside it, and I'll show a few examples of how thinking outside the visual spectrum actually enabled you to do a lot of things which you otherwise would not be able to do. So before I get into that, just wanted to talk about what a spectroscope is, and we have one of those here. So I guess you could pass it around and just look. So what a spectroscope really is nothing but a prism essentially, and a prism takes a single. So a prism is basically this optical element that bends any incoming ray of light. But the interesting thing is, because this is refraction, the refractive index of glass is actually slightly different. It's a function of the wavelength of light. So if you build a prism of the right material, right kind of glass, you can have it have a huge disparity in the refractive index between the 400 and 700 nanometers. And so when the light bends coming out of a prism, so it says grating here, but can be a prism or grating, any of those. When the light bends from here, the red, blue, and green, the different wavelengths, actually bend in different directions. And if you have a detector placed in front of it, you can sense the intensity of the blue ray, of the green ray, and of the red ray separately, and you can sort of decompose an incoming source of light into its constituents wavelengths.
Do you have a grating?
Yeah.
Okay. So I'll pass this around, and all you have to do is look through this hole here, and all it has is a slit in front. So the best way I found was to look at one of the bright lights up here, and very conveniently there is a scale on this side that goes from 400 nanometers to 700 nanometers. So the idea is that you can look at any point in the world and you can see its spectrum right away. So unfortunately we don't have like fluorescent lights. Actually we do. Yeah. Right. And you'll realize the fluorescence is actually very spiky. It has like sharp blue and then a little bit of green and red. Very, very annoying spectrum. It's not very nice and smooth like the sunlight. And I'll just pass it around. I was going to pass around the flashlighter, but not sure how many people have good hand-eye coordination. So there's
also this, which is a diffraction grating, and for the purpose of this dispersion, it's very similar to a prism. So if you look through this, you will be able to see a whole rainbow of colors around any sort of bright light behind it.
So when you're looking at this, look at it through a particular angle, a particular orientation, and then rotate it. And as you'll rotate, you'll realize that it will fall down.
Speaking of hand-eye
Exactly. I have an excuse. I was sick this week. You'll see that the image actually shifts around. So if I'm looking at Daniel, I see him, then I see a red copy of him and a blue copy of him. Shifted. Right? I knew there is more than one of you. And if I rotate, it rotates. And just remember this principle when we come back and talk, when Michael starts talking about different mechanisms for exploiting wavelength. Again, a great class project idea. Sorry, go ahead.
Yeah. So this here just shows one of a typical spectrogram kind of looks like. It's you have the wavelength over here and the intensity over here on the y-axis. So you can see there's like spikes over here at 550 nanometer, and then again 600 something. So this is probably a fluorescent light is kind of similar, I guess.
So maybe we can pass around this thing, LED light.
That might be very spiky.
Yeah, that'll be good to see. You can look at this, Sam.
Okay, so while one of you is looking, so this is stuff that Michael is going to get into much more detail later, but I just wanted to mention sort of, are you going to talk about the push chrome?
It won't hurt to do it twice, so go for it.
Okay, so I mean, it's just something which is very sort of high level of what he's actually going to talk about is the spectroscope is really imaging the multiple spectrums of a single point in space, like light source over here. If you have a full scene, you are not going to get much out of a spectroscope, and what you need to do then is what's called multispectral imaging or hyperspectral imaging, depending on how many spectrums you end up getting. And so there are these standard ways of doing that. And I just wanted to briefly mention what those are. So usually this kind of multispectral imaging is very popular in remote sensing kind of applications where you have a plane or a satellite that's flying over a region and you want to get the multispectral or hyperspectral image or data set of what's on the ground underneath. So what we have here is a lens kind of thing which is on the plane, image sensor behind it, and the object space which is on the ground. And so the most straightforward way of doing this is what's called so even this simple imaging where you're not imaging the complete spectrum, you can do it in various ways. The first way is where you have a lens which completely images the object space onto an image, a 2D sensor. So this is what just a traditional camera sort of looks like. You capture the whole scene in one go. Another way of doing this is what's called a push broom, and a push broom, the way I think of it, it's you're pushing forward as the platform or the plane is moving in that direction. So first, when the plane is at a particular location, you are imaging this line on the scene, and then in the next instant you will image this line, and then you will image this line, and so on. So as you're moving forward, you are imaging one line that's sort of directly under you. The other one is called the whisk broom, in which you are, while you're moving forward, you're going from left to right and from right to left, and you're doing this kind of a whisk broom kind of thing as opposed to a push broom. And what you do with this whisk broom is that when you are imaging this one element, you, instead of just imaging it onto one sensor, you pass the light through a prism and you get a whole spectrum similar to a spectroscope. And this gives you the complete spectral characteristics of this one element or one point on scene. And then in the next instant, you are going to sense the next element right next to it as your whisk broom is going from left to right, and so on. So you're going to sense the whole scene. The way the push broom hyperspectral sensor works is that so in this case you need just a 1D sensor in order to capture the complete data set of the hyperspectral image of the scene. Another way of doing it is using the push broom, where instead of so you put a prism in front of each of these elements, the image of each of these elements, and then you have a 2D sensor, and this 2D sensor would sense Along the x-axis is the point in space or the point in scene, and along the y-axis is the various spectral bands that you have for your hyperspectral imager. And then again, when in the next instant, you will sense the next sort of row in the scene. A third way of doing it is basically something that's similar to a traditional camera, is to put a filter in front of your lens and change the filter that's in front of your lens. Sort of either have that color wheel or have a tunable filter whose response is changing. But at any given instant, you're either sensing green, red, or blue, and then at the next instant, you're sensing the next one. It's similar to the first image we saw when I started the talk of capturing multiple images with different wavelength filters in front of the camera. It's similar to that. So you capture the whole scene in one instant, but only for one wavelength. So this sort of summarizes what I was talking about, that you have this what's called the data cube or the object cube, which is the x and y are the scene coordinates, x, y, and lambda is the wavelength where it goes from 400 to 700 or slightly beyond those extremes. You might also have near IR and so on. But this is what you want to get. And so this is a 3D sort of object, and unfortunately, your sensor can be at most a two-dimensional surface. So you want to somehow get this three-dimensional data set onto a two-dimensional sensor. And there are various ways in which you can do that. And the most traditional, most obvious way of doing it is to have the third dimension be time. So at any one given instant, you are either getting a slice like this, or a slice like this, or a slice like this, either along x, or along y, or along the wavelength. And that in the next instant you get the next slice, and so on. And then you combine all this information together. So over a period of time, you've built a complete object cube or data set. So this one is where you're using a filter, and this is where you're using a whisk broom or a push broom, depending on how you name them, x and y. So this is sort of the more traditional way of doing multispectral scanning, and Michael is going to talk about even more interesting, fancier ways of doing it by just taking projections, but I'll let him get into that. So I think Ramesh briefly mentioned thermal imaging, and can we get the lights off? So this is what, for those of you who've never seen a thermal camera, we have one upstairs. I think welcome to come and play with. But this is what images through a typical thermal imager or thermal camera look like. This is sensing usually in the wavelengths in the range of 1 micron to about 10 microns or 15 microns, in that range. That's the range in which humans show up as warm bodies usually. So 6 to 8 micron kind of range. But you can also have like actually hot bodies, warm bodies show up, like heat-seeking missiles and so on. But this is something that's explored a lot in the defense industry, these use of high-resolution, very fast thermal cameras. But it's something that's very rapidly coming into the other applications also. There was recently an article in Time, I think, in where they were looking at the various the thermal profile of a house from outside to find out where it's leaking and where the heat is escaping, and then they're using these kind of thermal cameras to actually test for whether pipes are leaking and your HVAC is working properly or not, and things like that. So it's finding lots of applications in areas other than just traditional defense and so on. And that's one of the reasons why slowly the price of these cameras, which used to be about $20,000 each, is hopefully coming down. This is sort of another image of just thermal images, which I thought was interesting. The first one is what's showing is that when you think of thermal light, it's actually quite different from when you're looking at visible light. And one example I think Ramesh already mentioned is that of glass. That glass appears opaque in thermal IR, so you can't look through glass. And there are other objects which may appear completely transparent in thermal IR but are opaque in visible light. This is one example which is sort of interesting. You have this fridge which is brushed metal, and so in the reflection you see this sort of very diffuse reflection. You can't really see what's on the other side. But if you just use thermal IR, you can very clearly see there is this rice oven sort of on the other side that's really, really hot, and the reflection is nice and sharp because the wavelength that you're using is now not 700 nanometers, but it's something much larger. And the surface is actually very smooth when you look at that wavelength. But when you're looking at it in the visible spectrum, it appears very diffuse and you can hardly see what the reflection is.
It's behaving like a mirror, basically.
It behaves like a mirror in the thermal thermal IR range because of the difference in wavelength. So this is sort of an interesting thing to think about of applications where you can imagine you had one of these thermal imaging cameras on each cell phone right next to your normal camera. What could you do with it? Or let's say you had it right next to your webcam on your laptop. Can you do something interesting with it? Another one is this paper from University of Colorado? No, Houston, right? Where they use thermal cameras to detect for light detection, and they have this paper in Nature where they analyze the region around the eyes and how that changes when someone is lying in the thermal IR range. And they claim that they're getting as good performance as a traditional lie detector.
It's not easy to reproduce, unfortunately, the results. But it looks pretty interesting. And the whole concept is that the blood veins pump more blood as your emotions change. So as long as you can detect subcutaneous changes in blood flow, you can detect the correlated emotions.
Yeah, I think the difference is really very, very subtle, and it's greatly magnified in this image that they show. So when we tried to do this, we couldn't spot any difference no matter what.
Of course, nobody lies in our group either.
So one other thing, when we were doing this last year, someone talked about near-infrared photography, and this is more from a photography point of view, that actually it turns out most of the CCD sensors are they're actually sensitive to near IR or infrared. That's just after the 700 nanometers, from 700 to about 1 micron. And they are sensitive to that, but in fact most manufacturers put an IR block filter on top of the sensor that blocks anything that's greater than 700 nanometers. So what you can do is remove that IR block filter, and you can then capture nice pretty images like this. This of course they're all fake images because you don't really get any sense of color once you go beyond 700 nanometers. So people usually just fill in fake colors based on an original visual image or something like that. But another place where you can get these colors is if you use IR film. There is Kodak has this color IR film which reacts differently to different wavelengths beyond the 700 nanometers, and that gives you these interesting sort of colors.
So these are not nighttime photos; these are just daytime photos with some pseudo color superimposed.
So the one interesting sort of thing is that I think sky becomes really, really black and opaque. So that's because if you remember, sky does not allow IR to come through as much. But also any vegetation becomes really bright and white, and that's sort of why you have the snow-like effect on trees and things like that. But your barks of the tree and the wood actually does not. It actually absorbs more light. It does not reflect so much back. So it's just interesting sort of things. And I mentioned this briefly earlier. One of the biggest applications of this sort of thing has traditionally been in remote sensing also. And by capturing multispectral or hyperspectral images of a scene of especially vegetation, you can actually classify what crop is what and what's the road and where you have plantations and what kind of plantations. Like over here, they're able to distinguish between all these different kind of crops. And this is something you can do if you have enough resolution in the multiple spectrums that you're getting, just because each sort of vegetation or tree actually has a very different reflectance profile when you look at it. Even though they both appear green to the human eye, if you look at the actual spectrum response, it's quite different, and you can distinguish between different materials based on that.
This is not based on IR though. This is visible spectrum.
I think it usually goes into near IR at least. Most of the remote sensing stuff, because I think most of the interesting stuff of this kind of distinguishing thing actually happens in near IR. But they do include visible light also.
They might have a band of 5 nanometers or 10 nanometers and capture 20, 30 channels. Okay. And then from that, in this high dimensional signal, they can do segmentation.
I'm not exactly sure. Do you know, Michael, what range they usually use for this kind of? Is it mid-IR?
Usually, I don't know usually, but it is definitely common to go into the IR and sometimes even into UV.
Right. So talking about UV, you can also do interesting sort of photography in the UV range, and this is an amazing website. If you get a chance, you should definitely visit it. This guy has like pictures of all kinds of flowers, and both in visible spectrum and then in UV, and it turns out that the flowers look just amazingly different when you look at them in UV, and you have these sort of landing strips that invite the bees to come and sit. They give directions, don't sit here, sit over here, kind of almost. Whereas if you look at it in the visible light, it's all yellow or it's all red, and there's hardly any difference between. You don't see that. Which
last one is especially striking.
Yeah. There's like portions which are pink. Well, again, this is all fake color. There really is no color in this UV. It's just the intensity. But one sort of thing I want to point out here is that you cannot do this sort of photography with most traditional cameras because glass is actually, it absorbs UV, so they use these special rare earth quartz lenses which are super expensive in order to do this kind of photography. Okay, so
but you could use, for example, what Professor Oliveira was talking about. Instead of using a lens, you could use a Fresnel zone plate, which is like a pinhole camera, except glorified. It has more interesting pattern. And then on the sensor, you could put a layer of fluorescent material, so that the UV will stimulate the fluorescent, and then make an image through that. So you can kind of go around some of the limitations in a traditional camera to do UV photography. And that's what they do in a way for a lot of medical imaging by using fluorescence.
Also, a lot of these images that you find, that they all use film photography. They rarely use digital cameras for these kind of things. I mean, even for near IR, I think.
This pseudo color, by the way, is just one of the major craze that has been around for several years. So remember, in the UV spectrum, these images are going to look just monochrome, just black and white. But artists like to start assigning some colors to different intensity levels to see more interesting. And for NASA and for astronomy, they realized it sometime about 20 years ago, that instead of putting those pictures of the nebulas and all that, instead of just putting them in this really boring monochrome colors, let's start coloring them. Beautiful reddish hues and greenish lavas and so on. Of course, the real thing doesn't look like that at all. But it allows ordinary people to start appreciating astronomy.
Yeah, it's like the wallpaper that comes with OS X has that. Okay, so now switching gears a little bit, this is more sort of getting into the human perception of color, and I'm not going to get into too many details, just a very high-level overview. So, have many of you looked at this figure before, this chromaticity diagram? So what this really this is the thing that people use in order to see how humans are actually sensing color, and what you have along over here is each of the spectrally pure colors, so going from 400 to 700 nanometers, and everything inside. So you have this blue over here going to green, and then red over here, and anything that's inside is basically a combination of multiple of these colors that are on the outside. So it turns out that most devices actually cannot. So this actually represents the space of all colors that the human eye can detect. It turns out that most devices actually occupy a much smaller space within this whole chromaticity diagram, this horseshoe-shaped thing. And so sRGB, which is sort of the default color of most CRT monitors, and it's the default color that's used on the internet, is actually a much smaller region. You can only represent colors that are in between this triangle in sRGB. Now, what's interesting with this color space is that once you have these three points, any point that's inside this triangle can actually be represented by a sum of just these three color primaries. So that's what I mean by fixed color primaries, that most cameras that have a single green, single red, and single blue filter on the sensor actually have the green is somewhere over here, blue is somewhere here, red is somewhere here, and that allows you to represent any color that lies within this triangle. Now, that's sort of what the color response of traditional film, and that's what it looks like for most cameras. So it's very similar. There is very little difference between the color response of the two. And in both cases, the response is made to closely mimic that of the human eye itself. Except for in film, where like this film, Belvia, I think, is something that's very good for nature photography, so they stress more on the red than what a digital camera does, just because it's a little unnatural, the colors coming out.
Belvia is for ocean photography. Like.
It's any landscape kind of thing, sunrises, sunsets, nature. It doesn't work very well for skin tone, for example. So this works fine as long as your color is within this triangle, but once you want to represent a color that's outside, it becomes, it's not possible to do that, because this RGB, the values can only be between 0 and 1. So there are a number of algorithms that you can use in order to estimate what the color should be, but each of them is sort of a lossy algorithm. You lose information because you may project it to the nearest point, or you may project it to the perceptually nearest point, and all those kind of things, but eventually you end up losing this information. So it turns out like all this region over here, it's very hard to represent colors over here just because your triangle is actually, it's outside this triangle. So one alternative you can do is that instead of putting your color primary over here, you can put your color primary out there. So now you have this really big color gamut, and you can represent all colors that lie inside this color space. Unfortunately, what that means is that your green is now very close to, let's say, 520 nanometers here. So it's a very spectrally pure. It's like just one very narrow range of wavelengths like that over there. And that means you have to use a very sharp wavelength profile LED or a laser or something of that sort if you're illuminating it, or a filter that's really dark. So it turns out that these optimal color gamuts that you have, they are a very good compromise between having a wide gamut and having filters that allow a large amount of power to come into the system. So if you have these primaries very close to the edges, you end up throwing away too much of the light. You get very little light coming in. So what you'd ideally want to do is have these sort of adaptive color primaries. So for a scene like this, you don't have too many reds in this. For example, you want color primaries to sort of be like this. That's just some arbitrary shape. And for a scene like this, you want them to be more like that. Rather than have the same set of color primaries for every image that you capture, you want to be a little more adaptive about it.
You may want to give the audio synthesizer analogy.
So it's kind of like the equalizer, you mean?
Yeah, equalizer.
So you want to be able to tweak the various wavelengths, what wavelength should be sensed more and what should be sensed less. And
so if you're playing, pop music versus classical music, you may want to change your synthesizer, more bass, less treble, and so on. And because those settings on your equalizer are also boosting certain frequencies and attenuating other frequencies. And in case of cameras, the RGB has already been fixed. There are exactly 3 points, and those 3 points have been fixed. But maybe you want to change them depending on the scene.
So that's what I'm going to briefly talk about, how one way of doing that. And is everyone aware? Have you talked about light fields?
Yes, talked about light fields.
I have a question.
Yeah.
So here in this graph, the chromaticity diagram, it seems like you can represent it in a 2D plane, right?
Yeah.
So which would mean that 2 primaries are enough to define any color, because it's just a 2D plane.
But there's also intensity.
There's intensity, which is sort of, this is a projection of the whole cube.
Oh, so it's actually a 3D thing, but...
Yeah.
Oh, okay.
Yeah.
Yeah.
But in terms of the color, you're right.
Yeah,
You
yeah.
could represent with two numbers, and the
Yeah.
third one is the intensity.
Okay.
And that's why you have LUV or LAB, where one is luminance and there's A and B, which is chromaticity A and
Okay.
chromaticity B.
Okay.
Or UV is the old one.
Oh.
Like one of the things that these, so this, when I said this is the RGB color space, this is actually incomplete. Just defining RGB is not enough. You need to define the white point inside. Where is the white? And that's sort of also something that's defined over there. And that, if you look in the third dimension, that's what represent the various levels of gray. So in order to represent the intensity, you need that third axis.
Mm-hmm.
And let me emphasize something that is easy to lose, I think, in this. We tend to use the words color and wavelength interchangeably in some situations. And wavelength is a truly physical phenomenon. It's a property of the universe, of the light itself. Color is specific to human vision, maybe other animals too, but it's different for them than it is for us. So when we talk about turning wavelength into color, what we're talking about is the process of human perception. And so this plot, for example, is specific to human vision. If it were some other creature or some physical device that we built, it would have a completely different plot.
Exactly. So here's a before we get on to the color sensing, here's the interesting puzzle. If you take a red laser pointer, which we're using red color for it now, and as Mike just reminded us, don't think of color, think of the wavelength. So let's say it has certain wavelength, I don't know, 680 nanometers, something like that?
630 probably.
630, okay. And if I just take the laser pointer and shine it in a, let's say, piece of water, piece of glass or a tank of water, okay, what's going to happen to it? So I have tank, I shine laser in it. What happens to it? It bends. Okay? And why does it bend? Does anything change about its physical properties? Of course it does. Either the wavelength or speed or frequency, something has to change. Right? The speed is actually decreasing. Right? So C in air versus C in water is related by a factor of what?
1.5.
The refractive index. Right? So this is actually reduced by a factor of 2/3. Now we know that here we have wavelength of light times the frequency of light. I'm just talking about A for air. This is for the laser. And similarly here we have wavelength in water times frequency in water. Right? So this has gone down by 2/3. Something here also has to go down by a factor of 2/3. Right? Yes?
So I'm getting frequency is fixed. So the
Yeah,
wavelength-
the frequency is
Right? So the wavelength has changed. So that means from 630 you said?
Sure.
From 630 we have gone down to 2/3 of that. So that would be what? 420. Right? So now this red laser is actually has a wavelength of 420 nanometers. And so we started from somewhere here, and the light wavelength is actually now even further down. So does it mean that when you shine a laser in water, it's actually blue? Because its wavelength now is 420 nanometers. Is it blue?
Well, we can't ever see that because we are, once it reaches the air, once it gets out of the water, it's
Uh-huh.
again.
Okay, so when it comes out, it's back to 630 again.
You could
But when it's inside, it's 420.
you could immerse a CCD in water, for example.
Okay.
I guess we sense frequency more than wavelength.
Very good.
That's exactly.
Right? So remember that message. Don't think about color. Think about the physical properties. And the way to think about that is you may have different wavelengths, but they mean different things in different media. In air, if you really want to think about colors, in air, 630 is red. In water, 420 is red.
So it gets too confusing. So you can use colors when they're convenient, but when you start talking about physical interaction, it's better to talk about wavelengths or really something that remains constant, which is frequency.
I think the important sort of thing is that the energy of the ray remains the same. It's E is equal to h nu, so where it's the frequency. So that's what the eye senses. It's the energy of the electrons that get displaced. But so that's why I said for whatever reasons, when you're talking about visible light, they always like to talk about it with wavelength, and it's not entirely correct because, as Ramesh pointed out, this figure is only true for air, and it would be completely very different if you were underwater. But it's just the convention that people like to follow, and that's what we're sticking to.
So you can always ask this question to your photographer friends, because they like to talk about colors.
So again, sort of going back over here, as I was saying, in different sort of, that's why they have both the frequency and the wavelength over here. In different fields and in for different purposes, you would use either frequency or wavelength. It's just that for photography and especially for this kind of imaging, and that too in the visible region, it's something that people usually use wavelength and not the frequency or the energy. So we want to try to come up with a way of having sort of adaptive color primaries. And so I'm going to go through a sort of analysis of an optical system that we developed, and everything that I'm going to discuss is going to be in what's called the flatland case. So it's just in 2 dimensions, but it scales up to a real 3D or 4D case also. So we start with a simple 1D signal, and this 1D signal is arbitrary intensity, and along this is the x position of the signal, and this is the intensity. And it's a white signal, which means it has all the visible frequencies between, let's say, 400 and 700 nanometers, and the intensity of each one of those wavelengths is actually the same. So that's what the wavelength profile or the color profile, spectral profile looks like at any point between A and C. So we take this signal and we put it in front of a pinhole. So here's your signal and here's the pinhole. So the pinhole essentially creates an inverted image of the signal. So you have this ABC here, you get A prime, B prime, C prime over here. It's just a pinhole camera. So now instead of positioning a film or a sensor over here, we put a lens in this plane, and this lens essentially collimates all these rays. So you have A prime, B prime, C prime. It's just like an orthographic sort of setup. So except it's inverted, which is not so important. But you have a ray coming in for each point in the scene. So next we place a prism in front of this, and now, as I mentioned earlier, that a prism actually bends the incoming ray, where the bending angle actually depends on the wavelength of light. So what I'm going to show for simplicity over here is that when you have a white light coming in, the ray corresponding to the green wavelength, or 550 nanometers or something, actually goes through straight, unbent. And red gets bent upwards and blue gets bent downwards. Now once again, I'm going against what Michael was saying. I'm calling it red, green and blue, but it really is the wavelength 400, 500 and 700 nanometers. I'm just going to call red, green and blue because it's easier to talk of it that way. And the other thing to notice here is that I'm only drawing these 3 rays, but really it's a whole fan of rays because it's a continuum and it's a white object.
The whole rainbow, basically.
You have the whole rainbow here. I'm just drawing 3 of those rays. So you would actually have a ray going down here and up there and anywhere between this blue and the red ray that we have. So now looking at this prism more closely, along this axis we have the spatial points of the scene. So you have A prime, B prime and C prime. And coming out of each of those points you have this wavelength angle, lambda. Now this figure should remind you of something, and anyone wants to guess? Like, does this figure look familiar to?
Assignment number.
Light field.
It's exactly like a light field, except the only difference is that instead of having theta over here or the angle, we replaced it with lambda. So this is something we call the spectral light field. It's instead of the angular light field or the spatial light field, it's the spectral light field. So any point over here in x or lambda will represent the intensity of a ray in this space coming out of some point along A and C and going in a particular direction. And since we started with a white light source, it's going to have the same intensity along each of these, along each wavelength. So now, since we've reduced this to nothing more than just a light field, it turns out we can use the various properties of a light field in analyzing the system. And the one, again, this is something that you should be familiar with if you know what a light field is that if you place a screen somewhere in front of a light field, you get a projection of the light field on that screen in a direction perpendicular to the screen in terms of the light field. So what that means in the flatline case is that now if I place a screen over here, this yellow thing, what that does to the light field is basically get a vertical projection, which is a direction perpendicular to the direction of the screen, which is along the x-axis. So what we are getting for every point over here is an integration over all the wavelengths for that particular x position. And you essentially get the shape of the signal in this projection. So if you were to place a screen over here, not surprisingly, you would get an image of the signal itself on the screen because it's so close to the prism. These rays haven't dispersed as much yet. It's almost the same thing as if there was no prism present over there. But now, as you move the screen away from the prism, the angle of projection changes and it becomes more, you get this shear sort of thing. And because of the shear, you get the various wavelengths, the signal corresponding to the different wavelengths is now dispersed and it's overlapping and shifted. And once again, I've shown just the blue, green, and red wavelengths here, but really it's a continuum, and you're getting this rainbow-like smear over here. And when you were looking through the diffraction grating, you could sort of almost see this. You get a rainbow coming out of every point when you look through it. And that's similar to what you're getting over here. Now, if you move this plane away to infinity, when it's at infinity, you're going to get this horizontal projection through the spectral light field. And now for each point on the screen, we are integrating over all the spatial positions, all the points on the signal for each wavelength. So what you get on the screen is nothing but a rainbow because we started with a white light source. And you have something going from blue to red. Any questions? So what we've done is that we have this one plane where if we put a screen on that plane, we get this spectral characteristics of the signal that we started with. So the problem with that, of course, is that this plane is infinitely far away, but we want to move it closer. So we place another lens in front of the prism. And this lens does two things. The first is that it creates a copy of the prism itself on this plane at some distance from the lens, where basically this is imaged, C prime is imaged at C double prime, B prime at B double prime, and so on. So similar to the X that you had there, you get an X over here. But you also get this plane in the middle where each ray for each scene point of a particular wavelength actually converges and meets at a point on this plane. So all the red rays are meeting here, green rays are meeting here, blue rays are meeting here, and so on. So once again, looking at this, when you place a screen at this plane at the end, which is an image of the prism itself, you're getting this vertical projection, and this is an image of the scene itself, and this is where we place our sensor, and we call this the sensor plane of the optical system. And if you look at this plane, which had this nice cute property of all the reds coming together, greens coming together, and so on, we actually get the horizontal projection, and this is the plane which was at infinity before. It's moved much closer than that, and you get this nice looking rainbow at this plane. We call this the rainbow plane. So the nice cute property of the rainbow plane is that all the rays of a given wavelength coming from all the points in the scene actually converge to a single unique point in this plane. So just to give you a couple of examples, if instead of the signal being white, if it had been completely red, let's say between 680 and 700 nanometers or something like that, when you took this horizontal projection at TR or at the rainbow plane, you would only get this part of the rainbow. You won't get the other remaining rainbow. Similarly, if your signal was half blue and half red, you would get something like this at the rainbow plane. So now if you place a mask in the rainbow plane, let's say you block out all these red rays that are going through, you actually put an occluder in that plane. When you, what that essentially does is that it multiplies the incoming light field at this plane, which is this, with a light field which is all zeros corresponding to the wavelengths that you block, and all ones corresponding to all the other wavelengths. And so what you get is basically this, what looks kind of like this. And now when you put the sensor at the screen at the sensor plane and you take the vertical projections, you don't get any of the red components, you only get the green and the blue components. So you essentially, by occluding the red channel over there, or the red color or the red wavelengths over there, you remove them from the light field that gets projected on the sensor, and you only get what looks like cyan. It's just green plus blue. If you were to do that to the green channel, if you just occlude that, you have a big zero over here, and you only get this plus this and this plus this, and so it looks magenta, and so on. So essentially what you can do is place any arbitrary mask you want in this rainbow plane, and that will influence what colors get sensed by the sensor and what colors are not sensed by the sensor. So by placing a mask in the rainbow plane, it allows you to control effectively the spectral sensitivity of the whole imaging system or the camera by modulating what rays go through and what rays get occluded over there. So that's what the whole sort of optical system looks like. We have the lens, the pinhole, the prism, another lens that images the rainbow plane, and we place a mask over there, and then the image sensor itself.
So what's the benefit of this and what's the disadvantage compared to the other schemes we have seen before? Let's look at the disadvantage first.
Well, starting with the pinhole.
That's a bad idea, yeah. It's always a bad idea. There is a pinhole, when you're blocking light, it's always a bad idea. So what would be, does everybody see that? What would happen if the pinhole was made larger?
Then you have to deal with focus problems again.
Blur.
Like goes everywhere.
So you'll get blur, but what kind of blur will you
Are
get?
you going to get blur between your spectrum pieces?
Exactly. The
yeah.
blur will be in the wavelength as opposed to in space. Because even if you make this pinhole larger, right, conceptually, I guess you're going to follow this trend?
Well,
Yeah.
no, that's it.
So, but just to get you thinking, if you increase that pinhole, you will still get an image at the end that looks sharp.
Yeah.
Just like an ordinary image, because we created two images. The prism plane is basically some kind of a virtual image. We formed an image on that, and the image of that is being formed on the sensor. So there's no problem in terms of defocus blur. But the ability to control specific wavelengths has now decreased. So there's a blur in terms of wavelengths, spectral copies, as Kevin was saying.
So what if we put some kind of like pattern to let in more light, but then we can deconvolve out later?
Some kind of coded aperture or something like that.
Or mask or anything.
Very good. Very good thing. We haven't covered coded aperture yet, so we'll do it.
Okay, I briefly talked about it in the end. But yeah, you're right. You could do something of that sort to deconvolve the effects of the blur arising from this. But it turns out that this is sort of a different kind of a trade-off that from what we saw earlier, like where we were doing the scanning in time. When you're scanning in time, it's almost like you have a pinhole in time, and then if you have scene motion, then you would have blur due to that. In this case, you have a pinhole in space, so you're getting all of this in one shot, but you're throwing away light over there because you need this. You can't have an infinitely a really large aperture, and you can have some sort of for a reasonably not very tiny aperture, you can get something like 6 or 10 different wavelengths over here, which is not great, but it's something that it gives you a control over. You can control the wavelength, the aperture size, and control the fidelity of the wavelengths that you're going to get here. So that's sort of the setup that we built. You have the image sensor over here, which is nothing but standard camera. This is the where we place the mask that controls what wavelengths go through and what don't, and then a bunch of lenses over here, and that's the diffraction grating that bends everything. So one thing you would notice is that there is a bend in the optical axis, something that I didn't show in the optical diagram so far, but it's again something you have to take care of if you're actually building the system. So, do you want me to go through all the examples, or
Yeah.
Okay. So this is a simple test setup that we built, and the idea was we had a spectral rainbow generator. So we have this rainbow which is going from red to blue. It's kind of like that, and then we are imaging this with this agile spectrum camera. Now notice that the color that you see here is because of the color of the bare sensor on the camera, and it's really, if you were to use a monochrome sensor, it would be all gray and just everything with equal intensity. So first, when we block off a certain wavelength, so let's say about 620 nanometers over here, you see a corresponding gap in the image that's captured by the camera, and it sort of gives you an intuition that it is blocking off in the right range, and the bare filter actually helps you see that here. And if you put some other arbitrary mask that's actually blocking off in two regions, you get a similar, a corresponding image on the sensor. It looks very different over here. It's like more blue over here and so on. So one of the applications you can do with this is this thing that we worked on was trying to reduce the glare coming out of this LED. So it's almost impossible to see here, but you actually have text written in the background, which is like some EG over here in the background, and then you have this bright LED in the foreground, and you want to be able to capture both the background and the foreground at the same time. And the background is much, much darker than the foreground. So if you were to do traditional sort of high dynamic range imaging, you would, if you increase the exposure much more, this halo that's coming out of this LED starts to occupy even more parts of the scene, and you can't really see the background. If you decrease the exposure, then this halo or this this artifact reduces, but then the background becomes even darker. So what you really want to do is just occlude this LED, the effect of the LED, and be able to see the background. And you can do that by, you still don't see it. So you can do that by blocking out these wavelengths corresponding to the LED. And now the LED is much dimmer. And actually, if you look at it over here, you can clearly read the background. So
this is strange. Now we can see barely. Wow, this projector is horrible.
Yeah.
So you can see the background a little bit over there better this way. So it's doing high dynamic range, but by modulating the spectral profile of the scene rather than by cutting off all wavelengths equally. You're cutting off just certain wavelengths that you know are in the scene that are causing this disturbance in the scene. So it turns out you can build a similar projector also. Instead of this was all for a camera, but you can also use this as a projection system. So now we have a traditional projector, diffraction rating, this lens, and then you have this arc plane where you have the mask, and then the screen is up there. And the advantage of doing it with this sort of a projector system is that you already have a pinhole, it turns out, inside the projector. And most projectors actually have a very long optical path between the light source and the projection lens in order to increase the depth of field that they get once they project the image. And it turns out we didn't even have to stop the lens or anything of that sort, and it just worked for a projector, a standard projector, without modifying it much. So this is sort of an acute example where the thing I wanted to mention over here is this concept of metamers. I don't know if that's been discussed. But metamer is two colors which appear the same to the human eye or a camera when viewed under a certain type of illumination. So this is the white illumination of the scene, and you probably can't see there's like this orange cloth there, blue cloth, and so on. And many of the colors over here, you can probably see it's very hard to distinguish between this dot and this envelope.
These
and
are
so
3M stickies, right?
Yeah, these are all sticky. So these are actually fluorescent, these envelopes, I think. And if you look on the... So if you look over here, you'll see as we project different wavelengths, how these colors, they appear almost black and very, very similar to one another under different illumination. And now one of them is going to become brighter than the other. And you can actually see the difference. So it's very interesting to see the progression of how it gives you an intuition into that there's much more to the wavelength profile than what the human eye simply sees in white light.
So can you just explain again what happened, during this animation?
Well, I'm just projecting monochromatic, sort of all very narrow wavelength of light.
So first is projecting red light.
It's monochromatic.
Yes. So red, green, and blue. So about 12 or 15 different wavelengths.
So it starts with very reddish, then slightly yellowish, then greenish, then magenta, and then finally bluish.
So
not magenta, sorry, cyan, and then bluish.
So it just shows you some of the... I think if you look at the background, this looks so different from this envelope, whereas over here it's actually very similar color in white light.
And these papers are very fluorescent intentionally, so they look very beautiful when they're on your tabletop. But they're also responding to very narrow wavelength of light. So that's why some of these envelopes become completely dark when you illuminate only a particular wavelength.
I have a question.
Yeah.
Could it have been possible for you to just take an image and then use different channels to generate those 15 images that you generated? Did you have to definitely take them at different illuminations, or
if you have a camera that captures all 15...
Or let us say just have an
broadband illumination. Those are the two things you need: broadband illumination and a camera that captures
all
many
the
spectrums.
15 spectrums.
Okay.
If you take only 3 spectrums,
Yeah.
then you only have 3 numbers per pixel.
Yeah.
So there's no way you can recover the 15. And if you have a camera like this, then a lot of other applications, like distinguishing between a fake vegetable and a real vegetable, and the freshness of skin, and looking through fog, all those problems, not fog maybe, but some other problems become manageable. And film and even digital photography is just trying to mimic human eye. 3 colors, in fact 3 fixed colors, as Ankit was saying. But what you really want is something like an audio equalizer. You can tune any frequency, any wavelength, so you can see the world in interesting ways.
So this is another example of where these adaptive color primaries would help. And as I mentioned earlier, there is very little... Like cyan is one of the hardest colors to project for most projectors, because your colors gamut is usually over there, and there's very little representation from there. And it turns out there are like 2 definitions of cyan. One is like the traditional printing cyan, and the other is what's called the electronic or electric cyan. And this color is, so what I'm projecting here is just a ramp between blue and green. So this is blue here and green and colors in between. And this is what the computer thinks of as cyan at the top and bottom. And you can see there's clearly a leak over here. And that's because when you, along this line is what I'm projecting over here, this line. And so this cyan is nothing but a point that lies somewhere on this line. So you cannot project a color which is out here using a standard projector or a display. But if you use this sort of agile spectrum, you can tweak it so that your color over here is actually something that's outside your color spectrum that the projector could have displayed. That's because you're not using the filters that the projector was using, but actually displaying something outside it.
So some companies also trying to sell you 4 or 6 color projectors. So they'll have this point here, maybe another point here, another point here, here, and here. So they can cover more colors than a standard 3 color projector. Because when it's a 3 color projector, you must pick some 3 points. And you cannot represent this shape with 3 points. If you start going too close to over here, if you take this point too close here, then as Ankit said earlier, it has to be very pure green. And that's difficult to generate unless you have a laser projector.
So do the laser projectors have a wider color gamut?
Exactly. So the laser projectors can go. They can stay almost on the pure color. So they can go all the way here and here and here. So they can cover a larger gamut. But there are other issues with them.
So they usually end up with higher contrast, but they are less brightness, or no? How do they usually fall?
No, they have good color rendition.
Yeah.
Contrast, I don't think there's any problem. No, there's no problem.
Okay.
Yeah. So in general, a laser projector is going to create a very nice rendition. It's just that it's not compatible directly with the human vision. So
Yeah, you get those
the
weird
sensitivity of the human
effects.
eye for pure color is not so great, unfortunately.
And there are some constraint in the wavelength that you can use. You can't just choose any wavelength. They have to have a very specific wavelength. Then they use frequency doublers or something to get the other colors. It's just a little more cumbersome to do that. And then there's the issue of power that you need if you want a laser projector to be bright enough. You need to have very bright lasers.
Yeah, the amount of optical power that a projector throws out compared to a typical laser is quite large. So these things actually put out a lot of power compared to your laser pointer, for example.
Right.
So putting a laser bright enough to generate this much light, that is challenging.
Yeah. Yeah. So I mean, this looks bright because it's illuminating just one point, the laser pointer. But if you were to actually distribute this over the whole region, you would barely see
Most
it.
of them are scanning
Sorry?
single point, aren't they? Aren't most laser projectors
Yes.
scanning
Exactly.
single point?
Yeah. So it's as though you're actually distributing this over the whole space.
So if you have 1 million pixels
You have to move
over one
really
frame,
rapidly.
every pixel is illuminated only 1/1,000,000th
That's
of a frame.
That's the trade-off,
Exactly.
right? Is you still need a lot of power,
Right.
Because you're not spending much time in any one place.
But they'll solve this problem. I'm very very hopeful that solid state lasers will.
But actually, that's a rough. If we assume for the moment that laser pointer is as bright as the red chunk of that slide you were showing us, like on the previous one, if it's roughly as bright, same ballpark, but that's roughly a megapixel image.
We need 1,000,000 times
We need
more.
about 1,000,000 times more power.
Yeah.
Which is true. This is about 1 milliwatt, and the projector is 250 watt. So it's 250 million times more the bulb, right, compared to this laser.
I think laser projectors work great if you are in this room where it's not too bright and you had the projector here projecting there kind of thing. It works reasonably well, but not if you have the lights on, you probably won't see anything. So another thing you can do with this is you don't, since you're not stuck with those 3 color primaries anymore. So this is just a scene. Again, it doesn't show up there as well. You have blue over here and you have yellow over here. And so traditionally you would have a RGB filter where for yellow you're turning it on when the red and the green color filter is in front of your projection, and for the blue you are turning it on only when the blue part of the color wheel is in front. But if you know that your scene has just this yellow and blue, you can actually just project you can use a yellow and blue projector, and you don't have to use the same traditional fixed color primaries. And this will give you a brighter scene and one that has more saturation also. So one other sort of cute example is that of color blindness simulation, and I know Professor Manuel has done a lot of work also in this area, I think. And the idea over here is, so one of the most popular type of color blindness is this difference, you can't tell the difference between red and green, and I think it's called deuteranope. And so when you have white light illumination, you can, I think on the right, again the lower ones are the deuteranope simulation, so you cannot tell the difference between the rows and the leaves, and they both appear the same color. Again, it's much easier to see over here. But if you actually project a certain wavelength of light on the object, it becomes much easier to tell the difference between these two, and you can again clearly see on the.
You don't have much luck here today.
Yeah, you can actually see the difference between those two when you have this certain projection. So conceivably using these kind of projections or using these kind of filters, you can help solve the problem. You can at least get some help in telling the difference between colors for people with color blindness. So, quickly go over some of the limitations. There's diffraction artifacts because you have a pinhole. You need a reasonably small f number in order to get large number or even some different color bands, and that's basically the limitations. And so future work, one of which you just mentioned, is actually using a mask over here, and I'll go into that just a little bit. And one sort of interesting, cute application, there's actually a company which does that, where they use this RGB wavelength multiplexing in order to do red and light, the red and right eye separation. So they project using
left and right.
Left and right. Sorry.
Red and right.
Left and right. And so they use these projectors which have, when you view them with a naked eye, both this and this appear blue because they're both in the blue wavelength, but they're actually different parts of the wavelength that's being occupied by those two projections. And if you put a color filter in front of your eyes, a different filter for each eye, you can have the red eye only see this part and the right eye see only that part. So when you view it visually, it would appear just like a normal projection, but if you put on the eyeglasses, you can actually distinguish between the two, and you can have sort of this multiplexing in wavelengths rather than in time or in polarization. So far we've talked about what's called the spectral light field, but it turns out you can actually combine the concept of a light field with the spectral light field. So what we have here is a traditional light field. Now it's x and theta, and you've placed a prism in front of this. So what this prism has done is, in a direction that depends on the distance between the x plane and the prism plane, you're actually going out and smearing it and getting all the wavelengths in that direction. So it gives you what looks kind of like that or something like that. So you have a whole bunch of overlapping spectral light fields on a spatial light field, or you can think of it the other way. You have a whole bunch of overlapping spatial light fields of a spectral light field. So, I mean, you can either put theta here and lambda here, or you can replace it and put lambda here and theta here, and it's really not very different. But what becomes interesting is the case where this plane is diffuse and frontoparallel, in which case each of these rays are exactly the same in density because it's a Lambertian or a diffuse scene. So in this case, what you get, the light field that you get over here is the special sort of light field that we call a blurred light field. It's because you're taking the standard spectral light field and then blurring it in this direction. So what you could do is, what Kevin was pointing out, is use, if this blurring is not just a box function but a special coded function, you could then invert that and you could get the full spectral light field out of it without having to use a pinhole. So this is what that design sort of looks like. So you can put, so before I get into that, one of the things I didn't talk about is, so you can, by putting a pinhole and putting a light field camera over here, you can simply, by using a standard light field camera, you can capture a multispectral image. So you can build a multispectral image by taking a light field camera and putting a prism, a lens, and a pinhole in front of it. So what you're essentially doing here is getting rid of the theta component of the light field and replacing it with the lambda component of the light field. So once again, you had this light field, and now you put a light field camera in front of it, you can sense that data. And this is sort of initial results that we had in that, where it's basically a micro lens array that's placed next to the sensor, and so you can see you still have the bare mosaic, so you have this red to blue sort of effect with green in between, which is what it's sensing. But another thing you can do is put what's called a linearly variable interference filter. So this filter allows only red wavelengths to come through at one end, green in the middle, and blue at the other end. And this is a very spectrally pure filter. It's basically built out of multiple layers of coating and using interference. And what this does is that it replaces the theta component of the light field with the lambda component of of the spectral light field. And now if you put a light field camera in front of it, you can again capture the complete light field, the complete multispectral image. The trade-off over here is that any one point on this filter allows only one very narrow wavelength to go through. So it's replacing a pinhole in space with a pinhole in wavelength. And so again, you're going to get very little light. But what you can also do is place, instead of that filter, you can place one of these carefully designed masks, which are similar to the mask we use in the coded aperture. But I guess we haven't talked about that.
No, we haven't talked.
So you can do this sort of thing and then use deconvolution in order to recover the multispectral image also.
Let's take a short break and then we can.
Okay, I just have this tomography stuff that you said I should.
Yeah, we'll do it after the break.
Okay, cool.
Cool, excellent.